Okay, hello everybody. I hope you can see my slides. Okay, then I will start with a live presentation. Well, how exciting, isn't it? So we've been working on MASQUE, and by we, I mean myself and my colleagues, Matthias, Magnus, and Marcus, and actually a few more people, but for this paper, we restricted people to a person whose first name starts with M, so that's where we are. Okay. That works. So what's MASQUE? MASQUE is basically a framework or a protocol for controlling QUIC, to use QUIC as a tunneling protocol. So there's a working group in the IETF, which is also called MASQUE, which is currently working on this kind of protocol. And effectively, it's an extension to the HTTP connect method we are using for proxying here. So with an HTTP3, we then allow to set up a QUIC tunnel in order to forward IP or UDP packets to a target server. So that's also what's shown in the picture here. What will happen is the client connects to a proxy with a QUIC connection and then tells the proxy to use this QUIC connection as the tunnel. We call this the outer QUIC connection. And then it requests the proxy to forward some other packets to an application or target server, which is then, might also be a QUIC connection, it could also be a different connection, which is, we call in our setup, it's always both of them are QUIC, so we call this the inner QUIC connection. And so this is the classical kind of VPN kind of scenario, but like you can do much more because you have this QUIC tunnel, which has multiplexing, so you can actually forward multiple streams to different application servers here using multiplexing in different streams, or you can also talk to the proxy using a separate stream and these kind of things. So this is why this is very interesting for us, and there are a bunch of use cases and different scenarios to connect data centers or in an access network or whatever, where this setup is actually beneficial. Before we start about the work, one thing that is also important to know about the setup is that QUIC supports as an extension also datagrams. So while QUIC streams are transmitted reliably, in this tunnel setup, it might be beneficial to actually use QUIC's datagram mode and not transmit the packets reliably over the QUIC tunnel because you already have reliability end-to-end. So in our setup, we evaluate both using streams where you have reliable transmission and using datagrams where you have unreliable transmission in the tunnel, in the outer QUIC connection. And we call this datagram and stream mode later on in the results. So what we did is basically two things. We implemented MASQUE in one of the existing QUIC stacks. We chose AOI QUIC because it's not like the best performant stack, I guess, but it's a Python stack. So it was actually very easy for us to prototype in this stack. And when we took this stack and integrated it into a Docker-based setup, which has exactly these three components to emulate some different network behaviors. So that's something you should keep in mind when you look at the results. We only implemented and we only evaluated one specific QUIC implementation here, and this might have performance implications. So if we look at different implementations, maybe the results might differ a little bit, but we also look not necessarily at performance results, but more general behaviors and implications. And then what we did with the setup is that we, as I just said, evaluated it in some basic network, under some basic network conditions. So this is just simply putting some delays and losses on the link between the client and the proxy, or using different packet sizes for QUIC. And we wanted to look at things like quantifying the overhead and the implications of this general setup, for example, for nested congestion control and these kind of things. So what we believe the study provides some interesting general findings about the setup. It doesn't tell you much about performance because the implementation isn't performant, but I think it's still good input to the ongoing standardization process. So that's why we're presenting it here. Okay, talking a little bit about our MASQUE implementation. So basically MASQUE has effectively three components here. One is the actual CONNECT-UDP method. This was when we implemented the draft, there was a separate HTTP method that was proposed. Today, it's more an extension to the existing connect HTTP method, but that actually doesn't matter. So, this is one part we implemented. And then also to get this running, you also need to implement something called HTTP datagrams. So this is just an HTTP extension to make use of QUIC datagrams for the datagram mode that I already explained. And there is a third part of it, which is the so-called capsule frames. So this is kind of an additional framework in MASQUE in order to register, for example, use of datagrams, or also provide any kind of other control information between the client and the proxy. So this looks in the picture, this looks like, it looks like as described basically in the picture, an application client would just open an end-to-end HTTP connection. So that's the connection that actually receives at the server at some point. But instead of having a UDP socket underneath, we have something that we call a MASQUE socket. And this MASQUE socket just opens another QUIC connection to a proxy, to the MASQUE proxy or MASQUE server here, and handles all the MASQUE specific additions needed here. So that's the green part that we implemented effectively. This is how our emulation setup looks like. As I said, it's Docker-based. We have 3 Docker containers, one for the client, one for the proxy, one for the server. And we have 2 networks, one between the client and the proxy, and one between the proxy and the server. And we use traffic control, simply traffic control, to just change certain parameters on these networks. In all scenarios, basically, the client sets up the tunnel connection to the proxy and then sets up an end-to-end QUIC connection to the server, and then requests to download a certain amount of data using HTTP. For the link between the proxy and the server, we have no bandwidth limitation, and we have a fixed one-way delay of 25 milliseconds for all scenarios. And the link between the client and the proxy, that's where we actually change the parameters. For the default settings, we usually have something like 10 Mbits per second, 5 milliseconds of delay, and quite large buffering of 200 milliseconds. So this is kind of a low bandwidth scenario, which maybe, looks like a today access network scenario, but probably the exact parameters don't matter that much because we vary some of them in some scenarios. Okay, let's start looking into some of the results. So the first thing we've been interested in is like kind of what's the overhead and what's the implication of that? Because if you have this tunnel, of course, you have some additional bits you have to transmit. And so we also looked at different MTU configurations. So what is marked here right now is basically giving you our default configuration, which is for the inner connection, we use an MTU or a packet size of 1280, which as said in the previous presentation, is the default minimum as defined for QUIC. And so what we do for the tunneling is we actually use a larger packet size in the tunnel setup. This is effectively can be realistic for access networks or whatever, but it's really just like for our testing, that was also the easiest solution. This is the default setting we use for both for datagrams and for streams. And like here in the picture, you can see whatever has an S at the end is in stream mode, and the first 2 results are in datagram mode in this picture. And in datagram mode, we actually have to use a larger outer packet size because we cannot split up the datagram over multiple outer packets. We have to fit it into one packet. In stream mode, we actually can do that. So in stream mode, we can even have this setup where we have like 1280 in both the inner and the outer, if like the local network or the network between the client and the proxy doesn't support a larger MTU. So now what does the graph tell you here? This graph on the left side gives you 2 values for what was observed at the proxy and what is observed at the target end-to-end server. Proxy in orange, end-to-end server in blue. And what you see here is what we call overhead in the terms of what's the additional data received at both of these points compared to the actual payload data that we were sending and defining in our HTTP request, right? So this is not only tunneling overhead, it's like all overhead, including the QUIC header, but also the QUIC header for the tunneling, all control data, and also the retransmissions. So if you look now at the datagram case first, you can see, for example, this difference between the datagram case and the stream case, where like the blue bar is just much bigger because in the datagram case, all the retransmissions are done end to end. So this is only the difference of the retransmission. But the interesting difference is still the difference between both the orange for the datagram and the orange for the stream mode, because that tells you a little bit that there's no overhead on the stream mode. Another interesting thing, or actually not that interesting because it's what is expected, is that if you use a larger MTU, then your transmission actually gets slightly faster. And we see kind of the same thing in datagram mode and in stream mode, but in stream mode, your transmission is actually quite a bit slower because you have more overhead and more dependencies. And then maybe just the last point here is also we tested these kind of more weird scenarios or different scenarios for stream mode. One scenario where you have the inner and the outer MTU both 280, or even like where you have the inner MTU larger than the outer MTU. That means you just have to split up the packets over more outer packets, and this introduces basically more overhead and makes your connection a little bit slower and also more diverse. So, you know, this is not unexpected, but it's nice to see this in the evaluation and see some data for it. Okay, let's talk about a slightly more interesting scenario. So in this scenario, instead of just having one inner connection to one server, we actually split it up data over multiple inner connections to potentially different servers. In our setup, we just send it to the same server because it was just easier for us to not change the setup. But in real life, it would potentially be to different servers, but over the same QUIC tunnel connection. And what we did here is that we always send the same or request the same amount of payload data, but we split it up over different connections to have it a little bit comparable. And this was not really expected. What we see here is somehow like when you have more connections, then somehow your transmission gets slower. And then, you know, the more you add, it gets kind of faster again. And like what was expected is that you have a little bit more overhead when you have more CONNECT-UDP requests, but that wasn't expected. And what we figured out when we actually looked at this loss graph here is that at least for stream mode, we've seen quite high losses for the cases where we have had 2 or 5 connections. And then we digged a little bit deeper and we figured out that this is actually spurious retransmissions effectively, because we have a lot of buffering in our proxy. We just like kind of have an infinite buffering. And the default scheduling that was implemented in IO QUIC just like takes always data from the first stream first and lets the other streams sit around and do nothing. And while this is not a general problem for QUIC in this proxy setup where you have different QUIC connection, it actually looks like losses for the other connection and they start retransmitting stuff. And that's why it takes so much longer. It doesn't really explain the UDP case because we had a very similar behavior, because there we didn't see the losses, but we still saw like a lot of increase, not the UDP case, sorry, the datagram case, but we still saw a lot of increase in the number of packets sent. And we are assuming that there's actual some kind of implications from the different congestion controls. So we believe that, for example, you probably get a very early loss and then you never open your congestion window to like the full speed. And so it just takes much longer. But this is something we really need to look into in more deep detail. Okay, one more set of graphs, but I will only talk very briefly about this. There's more information in the paper, but one thing I want to mention on this graph is also that this is one of the few graphs where we also have this data in here and what is marked in green now. And that's the case where we actually don't have any proxying, where we just send end-to-end data between the client and the proxy and the target server. And so you can see that in all cases, it's faster than using the proxy. And that is expected because if you just calculate the overhead from the tunneling and so on, it's more data to send, and we have like actually kind of low data scenarios here, so it has a quite big impact, but it actually only implements half of this difference. And what we also see here is, if you look at the right graph is that actually the loss rates for this end-to-end scenario is much higher. So what we do see here is again our effect of buffering. So while the loss rate is really here the end-to-end self-inflicted congestion losses, in our case we have so much buffering in the proxy that you like don't have a lot of losses but more buffering, and that actually increases also their transmission time. But there might be other effects, so we can look into this a little bit deeper as well at some point, hopefully in the future. Yeah, and then maybe one more thing to just peek on, like also future work here, is that this scenario was kind of interesting for us. So what we did in this scenario is vary the end-to-end delay between, not the end-to-end, the delay between the client and the proxy. And we had this one scenario where actually the delay between the client and the proxy was 50 milliseconds, so double the delay then between the client, the proxy and the server. And in that scenario, we got like very non-stable results. And we believe that in that scenario, you actually have effects of this nested congestion control, where you know, the loop of the outer congestion control is like already large part of the end-to-end delay. But we have to look further into that. Okay, one last graph, and this one I believe is easy to understand. So in this scenario, we did change the loss rate, or we did add additional artificial losses to the link between the client and the proxy. And so the first scenario is kind of the base scenario, no losses at all, where you see 0 loss rate. And then we added like 0.1, 1%, 2%, or 5% of losses. And I know 5% of losses is like very artificial and very high. But you can see that in this scenario, stream mode has actually huge benefits. Like we even have a demo running where you can watch a video when you have like these high loss rates and the video is just running nicely. So this is where you can do a big difference. And like I just said, this is kind of an artificial value, but it's only an artificial value because our access network and our lower layer technology is kind of already doing kind of repairing these losses and try to hide these losses. But if you can do this equally well on the higher layer, you can be more selective about where you need this loss repair and some additional delay and where you don't need it. So there might be a chance to kind of simplify the lower layers and move this functionality in the upper layer here. And it just like comes for free because you already have stream mode and QUIC. And if you have the setup deployed, you can just, you know, have it for free. So that's just a nice side effect. Not very surprising results, but good to see some numbers. Okay, so that was already what I wanted to present here. There's a little bit more data in the paper, but we also need to do more work. That became obvious, I believe. But what we did already is like having one implementation of MASQUE and getting it running in our environment. Hopefully we can do this with more implementations in the future as well and compare. Overall, we just tried to assess what is the overhead implications or other implications by using this kind of tunneling setup. And we found some really interesting effects. For example, the effect of using what kind of scheduling you're using in the proxy, which didn't work very well, which is easy to fix, but you have to be aware of it. You have to be careful here. There's also this implication for congestion control, where if you repair something locally, of course, your losses translate into delay, and that can have an implication on the end-to-end connection as well. But what we also don't know is really like any kind of implications that just come by this implementation and you know, can be fixed maybe in this implementation. So we definitely need to look into that. And as I said, I think this setup can actually provide some nice opportunities to, for example, simplify the lower link loss recovery or other kind of network functions and provide these functions in a way that the client actually can explicitly require and communicate with the network and request it. So that's why I think this setup is very interesting, and we will look further into it. Thank you very much.
Well, no, thank you. A very interesting presentation. I'm still working through it in my mind. Very, very interesting data points, some of which you also highlighted. Especially that interaction with the stream scheduling, the multiplexing scheduler chosen, and then leading that spurious loss in the congestion control. Very, very interesting stuff for me. There's one clarification question from Lucas in the chat. He asks for concurrent tunnels, if they were indeed served in a FIFO manner.
At the proxy, I'm not sure what he meant with concurrent tunnels.
Maybe Lucas wants to clarify. You can enable microphone if you want, Lucas. When you have multiple connect requests, instead.
So the problem is that the simple scheduling that is implemented in AO or QUIC is really just taking first all the data from stream 1. And if there's no more data on stream 1, then it takes data from other streams. So it's like not strictly a FIFO in the sense like it's not transmitted in the same way the data comes in, but on a per stream basis. And this is easy to fix, right? We just took a while to understand what's happening and what the problem is. Does that answer your question? Okay.
Yes. Anyone else have any questions for Miriam? I think later in the Apple keynote, we will also see that Apple has actually also deployed this in their private relay products already. And I think it will be very interesting to see if they, if you will talk about a few more of these aspects that they encountered.
Yeah,
well.
so that's definitely one of the very interesting use cases. And they even have a setup where they have two proxies. So they have one proxy basically at the access network side, and then they have another proxy which is close to the CDN network. So we could extend our scenario eventually and look at that as well.
For me, this is like a perfect example of something where academia can provide a lot of additional insights. These are very complex scenarios, at least to me. I don't know. I don't know to other people as well. For me, very complex and a lot of stuff to take into account here. We don't seem to have any other questions. So again, I'm going to ask my questions. I think you used QLog in this year as well. And I'm wondering if there are like major things you missed in QLog and or QVIS that help you debug this kind of distributed setup and how we might improve that. Do you have any opinions on that?
Yeah, so we only used the QLog as implemented in QUIC, and we used it for this basic kind of metrics like the round trip time, loss rates, and so on, right? So that was kind of straightforward. Of course, we were interested in not like debugging the exact event once something happens, but the aggregated data. So we had some post-processing added to it, but that's straightforward. But we didn't dig into these congestion control problems and so on. So we probably need to look into that further, and then you can ask me again.
Yeah, exactly. The point I'm just trying to make is that from that perspective as well, I think we laid the groundwork for this kind of tooling with QVIS, but there is so much more that still can be done to support this kind of much more complex scenario, right? Because QVIS now, I think, is woefully inadequate to help debug this kind of distributed thing. If you really want to have like a full view of the entire network with the different proxies, that is currently going to be a lot of work. So definitely, if people are interested in that, would be very useful, I think. All right. Have you played around with prioritizing, like using priorities in HTTP2 with the dependency tree? One of the ideas there was to make it sure that you can give some clients more bandwidth than others by using the dependency tree, and we threw that out in HTTP3. Do you have any comments on that, and how that might work in this kind of practical setup with MASQUE?
No, we didn't look at it at all. I mean, we didn't even fix a scheduling problem, which is probably easy to fix, but we just like took the implementation as it was and wanted to see what's happening. So we didn't look at this at all. Yeah,
but do you think that MASQUE, for example, will eventually add like a custom prioritization thing on top of what we have for H3 normal to re-enable this kind of stuff, or do you think that won't be necessary? Or
I don't know. So I think for the basic MASQUE case, not, but I can imagine that there are cases where the client wants to request certain services from the proxy, from the network effectively. And effectively, maybe it's just signaling a priority, or maybe it's actually more rich interface that would make sense. So I'm hope we're heading to that discussion, but I don't have any comments yet.
All right. Great. Then thanks again very much, Miriam and team, for what I thought was a very interesting presentation with these unexpected results. That
definitely, it was interesting for us, and as I say, we will continue. So thanks a lot.